Now at long last we're going to prove the forward direction of Hall's theorem. We're given a group G, and for all P dividing the order of G, the CeLO P subgroup has a complement. Then G is solvable. So the proof is by induction. So you write G in factored form, and you induct on two things. First, you induct on T, the number of prime factors, and then you induct on the order of G. So you can assume the statement's true for any smaller groups, or any groups with the same size that have fewer prime factors. Now, of course, the textbook doesn't state it that way, but I like to emphasize that because they do emphasize a few cases for smaller values of T. And so, for instance, case T equals 1. Then you have G as a P group. The statement about complements doesn't actually mean anything in that case. The complement is the trivial subgroup. So this condition hypothesis is always satisfied, but P groups are nilpotent, and nilpotent groups are solvable. So the conclusion already holds. Case T equals 2. G is a product of powers of 2 primes. The complement of a CeLO P1 subgroup would be a group of this order, P2 to the A2, which would be a CeLO P2 subgroup, which already exists by CeLO's theorem, and vice versa. So CeLO's theorem implies when T equals 2 that the CeLO P subgroups have complements. So we see the hypothesis is always satisfied for T equals 2. And then the conclusion should be that G is solvable. Oh, right, this is Burnside's theorem, which we already proved. So we're going to assume T is at least 3. And the goal, actually, is to find a non-trivial normal subgroup. And why would you want to do such a thing? Because then you could apply induction to n and G mod n, conclude that they're both solvable, and then use the fact that n is solvable and G mod n solvable implies G is solvable. But of course you can see there's a bit of a hiccup there. You actually have to prove that this hypothesis holds for n and G mod n in order to apply the induction hypothesis. Namely that CeLO P subgroups have complements in n and G mod n. So I'll focus on n for now. Let P be a CeLO P subgroup in n. Here I'm just assuming that a proper normal subgroup exists. We'll prove that such a thing happens in a moment. Well, P is a subgroup of G then. And so by one of the CELO theorems, if you let Q be the CELO P subgroup of G, then up to conjugation, GPG inverse is a subgroup of Q. That's one of the CELO theorems. Of course, since that part isn't quite as relevant, but the point is Q is a CELO P subgroup, and so Q has a complement. We'll call it H, which means H is a Hall subgroup. Then all you have to check by the previous lemma, H mod N is also a Hall subgroup. And by order considerations, H mod N is a complement to P. One can do the same thing with the quotient here. You take a CELO subgroup, you find a complement, it's a Hall subgroup, and so you can check that Hn mod n is also a Hall subgroup. And a P complement, CELO P complement. For G mod n. So every CELO P subgroup in N and every CELO P subgroup in G mod N does in fact have a complement. So you can apply the induction hypothesis. So all the hard work is going to be proving that a non-trivial normal subgroup actually exists. So now we're going to get into the nitty-gritty. We're going to let HI be a CELO PI complement. In other words, the order of HI is the order of G divided by the highest power of AI of P that you can divide, so that the GCD, or another way of stating it is so that PI no longer divides H. So the first thing we're going to do is prove that each of these groups themselves is solvable by using this theorem in induction. Seems kind of cheating to do that, but you can do it, so let's do it. And so what we're going to note is for all of J, 1 through T, except J is not I, the index of the intersection of HI and HJ in I is PJ to the AJ. This is using lemma 10, which remember has to do with what happens when you've got two subgroups in a group G, such that every highest power prime power dividing G, order of G, has to divide H or K. Then there was that thing, then that means G is equal to HK. And the size of H intersect K was this GCD of H and K. This is the part that's being used here. what this tells you, of course, is that what is the order of HI intersect HJ? Well, what is the GCD of these orders? You're missing 2 prime powers, so what are you looking at? You're looking at the order of G. Divide out PI to the AI, divide out PJ to the AJ. And so we see where this index comes from. We also now see that these two numbers are relatively prime. And so this tells you that HI intersect HJ is in fact a Hall subgroup. In HI. And is the PJ CeeLo PJ complement. In HI. In particular, for every J in this set, HI has a CeeLo PJ complement, which means the inductive hypothesis applies. Since each AI is solvable, in particular H1 is solvable, we can use the other lemmas we have to know that H1 has a normal subgroup with P a P group. And I is greater than 1. Now this is the first time we're going to take advantage of the fact that t is greater than 3, because we've now got two particular primes we're focusing on, P1 and Pi, and it turns out we need a third prime, say some Pj. So let j be any one of the other remaining numbers, except j is not I. So then what do we have next? Well, we look at H1 intersect Hj. It has order P2 to the A2, Pj minus 1 to the Aj minus 1, skip j. Up to Pt. Then the observation to note is that if you let, I guess we'll call it Q, be any CeeLo P subgroup in this intersection, Pi subgroup, by order considerations, Q is also CeeLo Pi subgroup in H1. Since P is actually a normal subgroup in H1, it follows that P is contained in Q. And this is for any Q, any CeeLo Pi subgroup in this intersection. In particular, Q was a subgroup of H1 intersect Hj. And so we now have P as a subgroup of H1 intersect Hj. This proof is very, very mysterious. What I'm going to emphasize here is the whole point in having P is that P guarantees that the normal subgroup we construct at the end is non-empty, or is non-trivial, because it's going to contain P as a subgroup. And P is a non-trivial subgroup because it's a P group, it has more than one element. That's the whole reason why we use it. If you don't have it, then it's not guaranteed that your construction results in a non-trivial normal subgroup. All right then, so where do we go from here? Well, by lemma 10, we're working only with these two groups now. G is equal to H1, Hj. And so every element in the larger group can be written as little h1, little hj. In particular, when you conjugate by an element in G, hj by this element in G, you end up getting the same answer as if you conjugated by a particular element from H1. And so that's going to tell us that when you intersect all of these conjugates of Hj, you actually get the same result as if you only take this intersection over H1. We'll see why we care about that in the moment. It's worth pointing out this is going to be our normal subgroup. It's clear that it's normal because it's an intersection of a bunch of conjugates, so it's closed under conjugation. So the only thing we actually need to show is that it's non-trivial. And that's the part where this is coming in. Because what we should have mentioned earlier is that actually P is a subgroup in Hj, even though we started with it being a normal subgroup in H1. And so we have P is actually a subgroup of all these conjugates. Because P is normal, when you conjugate P, you're going to get P back. And of course, P is only normal in the group H1, and that's why we needed to show this result, because we're only conjugating by elements in H1. And so, of course, since it's a subgroup of each of these conjugates, it's a subgroup of this intersection. Which means, congratulations, you have a subgroup of N. That is not the identity element, and N is a normal subgroup of G, therefore G actually is a proper normal subgroup. Also worth noting, because you're intersecting a bunch of conjugates of groups of the same size, and this size is less than G, the resulting intersection can have size G. So N is not equal to G either. So this really is proper.